All right. Hi, everybody. How's it going today? It's nice to see you all here. This is a pretty good crowd. I'm pretty excited about it. So my name is Ben. I'm an engineer here at Facebook. So I work here in London. We just opened an office here about 2 years ago, and so I moved over here to help start that office. So anyway, yeah, so I work here in London in our Covent Garden office. The main thing that I've worked on at Facebook is security. And what I want to talk to you guys about today is how we've approached security problems at Facebook. There's a whole host of common security problems that many websites run into, and we've spent a lot of time combating these. Obviously, Facebook is a really big target, and so we get a lot of attacks, but we have a lot of resources to deal with these. So I just want to talk about through some of the history of what we've done, what has worked for us, and what hasn't. So just to start off, we have this slogan at Facebook, which is you see kind of plastered around campus. It says, "Move fast and break things." The idea behind this slogan is we want to be able to ship products quickly. Okay, we want to get things done quickly, try things out, never stop moving, basically. And the break things part of this, what that really means is don't be afraid of making mistakes. Don't be afraid of failure. Don't be afraid of doing things wrong. The problem is there's certain areas, it's one thing if we have a bug in the site, it's one thing if a user is unable to upload a photo, but it's an entirely different thing if we have a security problem on the site or if we have a privacy problem on the site. So the goal of my team, or the team that I've been working on, is basically to help prevent these problems, to make sure that we don't have security problems that show up on the site, and that we enable our product engineers to actually build products and develop quickly and move fast. So there's kind of two main approaches that I'm going to be talking about throughout this talk. One is building good APIs. So APIs that are easy to use, that are really hard to get wrong, that take care of security problems as much as possible so that product engineers don't have to think about them, but also APIs that are really compelling. So APIs that are better to use than what the product engineers had before. So the idea being they should prefer to use these APIs versus the old broken things that they were using before. And then the other part of this, that's not going to catch everything. There's always going to be somebody who doesn't know about the API, somebody who uses the API wrong. So then the other part of this is always doing automatic detection to try to detect security problems that we have on the site. So we'll be talking about this with multiple kinds of vulnerabilities as we go through this talk today. One thing that I just want to mention before we get started is at Facebook, we have a monolithic code base. So we have one giant PHP code base that contains most of the code for the site, most of the business logic, most of the code for rendering HTML and all of that. There's a bunch of backend services behind that, but the PHP code base is the heart of what we do. And it's giant. It's, together with the Git directory, it's something like 49 gigabytes. So it's quite a lot to have, but there are some really huge advantages to this, which is especially in terms of security, if we want to make a security change to the site, it's really easy to do that in one place and have that affect the entire website and push that out quickly. With this code base, we're doing pushes twice a day regularly, so it's pretty easy to push something out and make changes and make fixes on the website. So this has been a huge help for us in terms of security. So that being said, let's jump into the first vulnerability that I want to talk about, which is cross-site scripting. So this is a pretty standard vulnerability. This is something that you see on a lot of websites. And this is, the basic pattern that you see that's dangerous is somebody is building up a piece of HTML, and they have some, user data that they are concatenating into an HTML tag that they're building up here. And the problem is if you just stick user data in there, that allows people to execute arbitrary JavaScript. And if they can execute arbitrary JavaScript, then they can take over users' accounts and they can do whatever they want with those accounts. So this is a really bad flaw, and unfortunately it's really common on the web. But anyway, the first solution that we adopted at Facebook was basically what I would call manual escaping. So everybody goes through, and when they're building up a piece of HTML, they call HTML special chars, and they escape all the dangerous characters. So they get rid of the less thans and the greater thans and all that stuff. And this makes your HTML safe. The problem is this is not a very scalable solution to building safe HTML. If you have a bunch of engineers who are writing code like this, there's two problems. They might forget to do it, so you need really good code reviews to make sure that people do it right. The other problem is that eventually you start passing pieces of HTML around your site, or between different functions. So you'll have a bunch of strings floating around your code base, some of which are safe pieces of HTML, and some strings of which are unsafe data that came from the user. And it's really hard in a large code base to tell the difference between the two. When you look at a string, it's really hard to see, is this safe or is this unsafe? And so as your code base gets bigger and bigger, it's harder and harder to keep track of this, and it's harder and harder to make sure that you're escaping everything. So this was not a great solution for us. We went with it for a while, but eventually we just realized that it wasn't working very well for us. So the thing that we actually do now is a system called XHP. So XHP allows us to stick HTML tags directly into our PHP source code. Those get transformed into objects, and XHP handles all of the escaping under the covers. So basically product engineers don't have to think about this at all. They don't have to think about when do I need to escape and when do I not. XHP keeps track of all of this automatically. And basically the assumption that it makes is if you have a string, any string is unsafe. Okay? Any string that we have in the code base is assumed to be user data that is not allowed to be output. And then on the other hand, if it's HTML, if it's a safe piece of HTML, it's actually an object. So we can distinguish between these in our code base, which is really, really helpful. So, and the thing about this API is, if you compare the way that we write code now with a simple HTML tag versus the stuff that we were doing before with string concatenation, it's clear that this XHP is just a much more compelling API. So it's much easier for product engineers to use. It's much easier to see the code, and they don't have to spend their time worrying about security. So this is basically a win for everybody. It allows the product engineers to move quickly, and it makes sure that we have security and that we don't have XSS on the site. And we do a similar thing in JavaScript as well that allows us to just put HTML tags directly into our JavaScript. So that was great. When we introduced this, we introduced this, I don't know, 5 years ago or something like that, and most of the site is now built using this XHP. The thing is, we always have legacy code. Even today, we still have code that was written, endpoints that were created more than 5 years ago. So the question is, how do we detect those issues, any XSS holes that we had before we switched over to XHP? And for that, we use a bit of automated XSS detection. So we have this thing called XSS detector, and basically, we use a little trick while we're doing our escaping. So basically, normally when you're escaping characters, you only escape less than, greater than, quotes, things like that. In our case, when we turn the detector on, we also escape the letter E, and we turn it into this code #101, ampersand #101 semicolon. And to the browser, this renders as an E. When it gets to the browser and it gets displayed, it actually shows up as an E. So to the user, it doesn't change anything. But what this allows us to do is, at the end of the page, when we're sending the output back to the user, we can scan through the whole HTML and we can say, oh, okay, so we found a lowercase e character here. And if we ever find a lowercase e, that means that was something that we didn't escape, that didn't actually go through the escaping function. So this is a pretty clever trick that allowed us to basically find most of the XSS holes that existed before we switched over to XHP. And basically, we continue to run this. Basically, we don't run it on every request. We run it on some small fraction of requests, maybe 1 out of a million requests or something like that. And it does depend. It's kind of a random system for finding XSS holes in that it only finds an XSS hole if there happens to be an E in that location. But overall, you run this on enough requests, and it works out pretty well. We ran into some funny problems with this system, though. One example was Japanese mobile phones. Here's what our composer should look like on the left, and then on the right, when it was rendered on one of these mobile phones, it turned out the composer had all these hidden input fields shown. And what it turned out was some of these mobile phones, they did not properly handle having an escaped E inside of an input tag that said type equals hidden. So this was kind of a clever thing, or kind of a funny problem. But anyway, what we ended up doing is adding a final pass. Basically, after we check the output and we make sure that there's no XSS holes, we remove all these special codes and we change it back to an E so that it's all normal to the browser, basically. But anyway, this has worked out really well for us, this whole system. So again, with XSS, there's these two approaches, right? There's the better API that's easy to use and works out better for everyone. And then on the other hand, there's automatic enforcement trying to find XSS holes. So one interesting attack that we've run across, I don't know that we've ever actually seen this in the wild, but this is something that one of our engineers, that we've seen like people post about, and one of our engineers figured out how you could apply it to Facebook, is something called character set reinterpretation. And the idea behind this attack is if you can convince the user to change the character set in their browser, that can actually cause a security hole. So in this instance, well, in this example that I'm going to give, basically we have an input tag that has a value that has a Japanese character in it, the Japanese character ku. And if you do this, if you give them this code or output this code somehow, and then you tell the user, okay, switch your character set from UTF-8, which is what we normally use on Facebook. If you switch it from UTF-8 to EUC-JP, then the browser starts misparsing this. And what normally this ku is 3 bytes in UTF-8, and then the quote is 1 byte. But when you switch to EUC-JP, then you end up with the browser parsing it as 2 bytes and 2 bytes. And so it completely misses the close quote character in this tag, which gives an attacker an opportunity to go through and insert some JavaScript later on in the tag. This is a pretty clever attack, and as I said, I don't think we've ever seen this in the wild, but we still didn't want to leave this as a possibility. So what we actually ended up doing was escaping those non-ASCII characters. So what we do is in any HTML tag, if you have something that's not an ASCII character, it gets escaped into its HTML entity form. So there's basically no way, the character set doesn't matter anymore. As long as we all agree that on the base ASCII characters, it's fine. And again, this is, I think a lot of modern browsers deal with this. They actually handle this, and it's not really a problem. Like if we say UTF-8, the browser doesn't let the user change it anymore. But this is something, it's like nice to be able to protect against these things. And XHP made this really simple because we had this one uniform place where we could escape everything, where we could just basically make one line change and say, okay, when we're doing an attribute, do this. But we don't want to do it for body text. Like most of the body text on the site, body text doesn't have this problem because there's no quotes to be aware of. So we just decided, okay, body text doesn't matter, and we can only do this for attributes and save us some, so we're not adding too many more bytes to the page. Okay, so that's XSS. So let's move on to another vulnerability. So SQL injection. Hopefully this is also really well known and everybody knows all about SQL injection and how this works. XKCD really helped with this process. So, again, it's the same problem. You're building up something, you're building up a SQL query, and you're sticking user data in there, and if you're not careful about the user data you put in there, then the person can break out and start executing whatever SQL queries they want. So our first approach here was something that we call parameterized SQL. So this looks a little bit like printf. We have all these percent encodings that you can put into your query. So you can say, for instance, %s, I want to stick a string here in the query, and then you give the argument. And obviously this is not like printf. If you did this with printf, it would be horribly unsafe because you wouldn't, it would be a SQL injection hole. But this function automatically handles the escaping. If there's a quote in the string, for instance, it puts a backslash before it, and then it's fine. So this is fine. This worked out pretty well for us for a while. But again, and actually, it's a really compelling API. So one thing about this is we have a lot of specialized conversions that let you do things really easily in SQL. Like if you want to put a list of integers, or you have a map of key names to values, and you want to turn that into a where clause, we have a specialized thing, %w, that does that for you. So there's a lot of really nice tricks that make it really easy to build up SQL queries using this API. So again, the problem with this API though, so it's got the compelling part going for it, and it's pretty safe if you use it correctly, but it is a bit hard to prevent misuse of this API. So in particular, there's nothing that prevents people from doing their own string concatenation and just shoving user data into the query somewhere. So if somebody does this, if they, one common pattern when you're building up a SQL query, at least in our code base, one common pattern is that people want to start by building up a where clause, and then they want to, and they'll maybe build that up piece by piece, and then they'll stick that into a larger select statement somewhere. And so this kind of, when you end up having the SQL query built up across multiple lines, it can be easy to make mistakes like this, where you shove some user data in there. And there was no way for us to find this, basically. So the better way that you were supposed to do this was something you basically would call a function. This was kind of like HTML special chars all over again. You would call your escaping function, and you would build up the where clause as a string. You would build a safe string for the where clause, and then you would shove that into your query using %q, which is a special thing that allows you to shove other bits of query in there. So this is all right. Like again, you can make this safe, but it's still not perfect because we still can't tell, okay, is this a safe query or is this unsafe? So what we ended up switching to, the newest thing is we have switched over to objects. So this is basically the same solution for SQL that we had for XHP. Instead of passing a bunch of strings around, instead of having SQL strings and unsafe strings, instead of having HTML strings and unsafe strings, what we've done is turned everything into an object. So you have SQL objects, and then if it's a string, again, we just assume that all strings are unsafe, and they have not been escaped yet. So what's great about this API, so you can build up your query piece by piece. You can create a where clause, and that's so you can create a fragment of a query, and that can be an SQL object. What we enforce with this is the first argument to this SQL query, for instance, this format string here, this always has to be a constant string in the code base. So you're not allowed to stick any variables in there. You're not allowed to do, concatenate any variables in there. And that's how we show that. So there's basically a lint rule that says you may not do that. So with that, that's how we guarantee that there are no SQL injection holes in the code base. This format string, we know that the format string is a constant string, and then we know that any of the other arguments that you pass into the SQL function, like the email parameter, the where clause, we know those are going to be escaped correctly. And down here with the %q down here, we can say, okay, %q, whenever we have %q, that has to be a SQL object that's being passed in. So again, we can sort of tighten the whole thing up, and we can make sure that there's no way for unsafe data to get in there. So this has been a pretty compelling API, and it works pretty well. One question you might have is, why not use prepared SQL statements? Prepared SQL statements are a very common suggestion for how to avoid SQL injection. There's kind of a few reasons for this. One is that in some cases, prepared statements take an extra round trip to prepare, which may not be a problem for if you have a small website. That's probably not a problem. For us, our databases may be located in a different data center or something, so those round trips are actually really painful for us. The other thing is, as I mentioned, all those other type conversions that we have a bunch of type conversions for comments, for table names, for building up where clauses and lists of integers and all of this. And it makes a very rich API compared to the standard prepared SQL statement API. So this is why we've gone with that. So beyond that, though, of course, the thing is we've tried to really avoid SQL in the first place. At Facebook, we have a bunch of, there's a bunch of internal tools and things that are still built using SQL queries. But really what we've tried to do is move towards a social graph model, a graph data model. So basically what we have is we have a bunch of nodes in our graph, or objects, and each object can be connected to other objects using what we call associations, which are edges in the graph. And so we have this nice API that lets you create nodes, that lets you create edges, and there's basically no way that you can have any sort of injection attack against that. You're not writing SQL queries anymore. You just specify, this is the data that I want to put in there, and the low-level functions take care of all of the escaping. So honestly, this is the best way to take care of SQL problem, SQL injection, is to stop having your developers write SQL. But that's not always possible. But for us, we've found a way, and it has actually, this has had a lot of benefits for us in terms of how we've designed our site. So product engineers just never write SQL now. Okay, so let's move on to our third security problem. So cross-site request forgery. So the idea behind cross-site request forgery, for those of you who don't know, the idea is when you as a website, when you receive a request, you don't know for sure whether the user actually intended to make that request or not. So what I mean is an attacker can put some code on their site that sends requests to facebook.com. And so if a user goes and visits that attacker website, and the attacker website triggers some requests to Facebook, your browser will happily send along all the cookies for facebook.com. And when we get that request, we get those cookies, and it looks to us like the user's logged in. I mean, the user is logged in. And the problem is, we don't know, did the user, when they made this action, did they come from facebook.com? Were they on Facebook and they clicked a like button? Or were they on this attacker site and the attacker's website sent this request to Facebook? So The usual answer here for CSRF is you add a CSRF token to everything. Okay, so every form has a hidden element that contains this little secret code. And the secret code, it's a different secret code for every user, so it's not possible, like basically the attacker doesn't have any idea. The attacker can't predict what this code is, so they can't send it when they make the request. So this allows us to distinguish between legitimate requests that came from Facebook.com, where the user actually clicked the like button, because that will have the token, versus something that came from the attacker, where that will not have the token. So the first thing that we did a long time ago, 6 years ago or something like that, we were doing all manual checks of our tokens. So this was really awful. Basically, every endpoint started like this. You would include your libraries, you would check who the logged in user was, and then you would check, okay, does this request have a CSRF token attached to it? And this is basically, again, this is like all of the other things we've talked about. If you have really good code reviews, if you have a bunch of product engineers who really understand security, you can make this work. It is possible. But you're probably going to forget something. I mean, with enough people with enough time, you're going to forget to add this check somewhere. So what we realized is that we needed to be checking this automatically. So back in, I don't know, 2009 or something like that, we decided to turn on automatic enforcement for CSRF tokens. And the way that we divided this was we had GET requests on one side and POST requests on the other. So GET requests, basically GET requests, they don't have to have a token. Okay, a GET request is just somebody coming to read data from the site, but a GET request is also not allowed to write any data on the site. So what we did was we added checks in all of our low-level, our database functions and anything else that did a write. We added a check in there to say, yes, this is a POST request. This only works if it's a POST request. It doesn't work if it's a GET request. Okay. So, and then POST requests, on the other hand, we automatically checked at the beginning of every POST request, okay, you must have a CSRF token. And then once you have that, okay, it's fine, you can go do writes. So this was a huge step forward for us, and it cleared up a lot of CSRF problems. The only problem with this is you have to go through and instrument every single thing that might do a write. Some of these are really straightforward. The database calls, those are pretty straightforward. When somebody makes a database query, you can just look at the database query and say, okay, this is a select statement. Sorry, this is a select statement, so obviously that's just a read, that's fine. Or this is an insert or an update or whatever, and so that's a write statement, and so you're not allowed to do that on a GET request. But there are other things that just don't, where it's harder to tell. Okay, so we have a lot of backend services at Facebook, and it's hard to tell when somebody makes a request to a backend. Are they just reading data? Or are they trying to do something? Like, as an example, our messages are all stored in a separate service. And so whenever you send a message, you're sending this request off to the messages service. And the question is, how do you know, did the person, are you reading messages or are you writing messages? So you have to go in, and there's always things that you're going to miss when you do this. And so what we ended up doing is adding a second layer of protection. And so the second layer is every endpoint controller on the site must declare, is it a read endpoint or is it a write endpoint? And again, the same rules apply. If it's a read endpoint, you're not allowed to do any database writes. You don't need the CSRF token, all of that. But if it's a write endpoint, then you are allowed to, and you get the CSRF, you have to have the CSRF token and all that. So with these two things combined, that lets us prevent most CSRF problems. There's a final thing that we can do in modern browsers. So some modern browsers anyway, they send an origin header. So the origin header says basically where the request came from. So in one of these modern browsers, if an attacker, if evil.com tries to send a request over to Facebook, then the origin header will say evil.com, and we can just reject the request. So that helps us a little bit, but we still need all this other stuff because there are older browsers that just don't do that. So anyway, this is all great. This automatic enforcement is great, except that there are always times when people need to work around it. I wish we could live in a perfect world where everybody, nobody did any writes on a GET request, but that's just not true. That's just not how the world works. There's a couple reasons why people might need to do writes during a GET request. So one example would be if there are certain pages on Facebook, we keep track of the last time you visited that page so that we can show you, oh, hey, here are the new things that showed up since the last time you were here. So for those pages, we need to write something every time you visit the page so we can keep track of that. Another example is There's some cases where we lazily create data the first time that you try to read it. So there are some as an example, we have some random parameters that are used, like parameters where for each user, we generate a random value. And we don't generate that random value when you create the account. We generate it the first time that you ever need it, the first time that you try to read it. And so that's a case where you're reading data, but actually you need to write something back to the database. So the way that we deal with these, or the original way that we dealt with these, is something called a scope guard. And so the idea of a scope guard is, you've got this little section of code where you know, okay, I'm going to do something. I'm going to cheat a little bit, and I'm going to do it right, even though it's a GET request. So we had this way of saying, okay, you grab this guard, and as long as from the time that you create the guard until the time that you call release, you are allowed to do any writes to the databases. So we gave it a really scary name because we found that product engineers, if we didn't give it a scary name, they would just call it, they would just get some error, they would get a CSRF error, and they would just add the guard somewhere because they just wanted to make their product work. So we needed to make it a really scary name to make sure that they understood what the consequences were of what they were doing. Now the problem that happens with scope guards is it's really hard to figure out where to put these scope guards in your stack. So if you think about this from the top of your stack being an endpoint controller and the bottom being your low-level database access functions, if you put the guard too high in your stack, if you put it in an endpoint controller, then you would allow any writes to happen in that endpoint controller. So that's obviously too high. And if you put it all the way in the low-level database access, then you would allow any writes to happen on the site anywhere. So you have to find this weird middle ground that is a logging function or something like that, where okay, everything going through here is safe. And it's really hard to make sure that you choose the right place. It's hard for me as a security engineer to choose that place. It's even harder for our product engineers who don't think about this every day to choose that place. So it's a really difficult problem to put the scope guard in the right place. The other thing is, as we've gone along, we've moved towards more of an event-driven model for programming at Facebook. And so we have this feature called asynchronous functions, which is basically a form of coroutines that we use in Facebook. If you've used C#, you might recognize this syntax. It's quite similar to C#. But basically, we have a special keyword called await. And what await does is it says, okay, I've got some long operation that I want to run. So when I hit the await, just stop executing me, go off and execute some other stuff, and then when that long-running operation finishes, come back and start running me again from this point. So in this case, you might have one function that grabs a guard and is trying to write some data. But then, because that write takes a long time, we switch to a completely different function. And then it tries to do a write. And the thing is, this write, the guard is there. I mean, the guard is a global variable. So the guard, basically, it doesn't matter. The global variable takes effect for both of these functions at the same time because they're kind of being run simultaneously. I mean, this is still a single-threaded system, to be clear, but because we're switching back and forth between different functions, this global variable model doesn't work very well at all. So this was another reason why we had to abandon guards. Guards just don't work for us in our code base anymore. So what we ended up doing is we realized really what we wanted. It's not really, we don't want to specify a specific code path that's safe or that is allowed to write. Generally, what we want to do is we want to specify a specific type of data that's allowed to be written. So we want to say something like, okay, we've got a database table, and all of the data in this table is logging data. Or we've got a specific type of object in the graph, and this object is always, it's a special kind of data that we create lazily. And so we switch to a whitelist where we basically say, okay, these database tables, these node types, these edge types, you're allowed to write to those on a GET request. And this has been much more scalable for us. It doesn't have any of the problems with async functions. It doesn't have any of the problems with trying to figure out where to put the guard in your code base. There's still some cases where we need solutions like what we had back there, but this has worked out so much better for us, and it's been a huge help. Okay. So next thing. So cryptography. So cryptography is a fun example because there's a really clear example of a case where Facebook did this wrong and it caused problems. So this was, again, a really long time ago. Most of my stories come from a long time ago when we didn't have as good of a security team back then. But basically, there's this feature that we have on Facebook called public photo links. And the idea of a public photo link is that you might have an album or something on Facebook or a photo that you want to share with somebody who doesn't actually have a Facebook account. And so in order to enable that, we have this way of generating a public photo link that has a special hash. And that hash says, basically gives authentication that allows the person to see the album. Well, so back in 2009, this is what our links looked like. The hash was 5 characters. It was a hexadecimal string. If you do the math, that's 20 bits. That's only 1 million possibilities for this hash. So basically what some guy figured out that you could just go through these one by one, try every single possible hash until you found the one that worked. And he wrote a blog post about it, how you could basically see anybody's photos. And it wasn't fast. It took a little bit of time to run all these requests, but it was still a really bad privacy problem for us. So what's interesting is if you go and look at the function that does this, that generated this code, it has a huge number of examples of things that we did wrong with the cryptography. So here's the function that we were using. So basically, what you had is we were getting a secret parameter for the user, because obviously these photo links need to be different for every user. And then we were doing an MD5, and then we were taking the first 5 characters from the MD5. So the first problem, of course, we were taking only 5 characters. So that was really bad. That's what allowed the person to iterate through all of them and try all 1 million possibilities. So the next thing, there's a hard-coded secret in here. So hard-coded secrets are generally bad in your source code because, first of all, somebody might get a hold of your source code. Like your source code, at least we try to assume that at Facebook that our source code eventually is going to leak and that somebody is going to see it. So we shouldn't put secrets in here. We should put secrets somewhere else where we can actually protect them. The other thing is if you ever want to change the secret, if the secret does get leaked, you want a process in place for how to change that without completely disrupting everybody that's currently using the service. And basically, there's no way to rotate this secret safely the way this function is written. Then there's the fact that it's using MD5, which is an old hash function. It's not completely broken, but there's a lot of known vulnerabilities in MD5, and so it's just not a good idea to use it in new code. And then there's the fact that this is a regular hash. It's just a straight hash of the data rather than an HMAC. So when you're doing any sort of, this is essentially what we would call a message authentication code. And in that case, you need to use an HMAC algorithm rather than doing this hash itself. Because there have been attacks. There's something called a length extension attack you can do on an MD5, which, anyway, has actually affected other services. But anyway, this is just not a good strategy for building. Like there's just a surprising number of things wrong with this function. So what we ended up doing is building a library to take care of this for us. So basically, again, the idea was let's build an API that is super easy to use, that is way easier than writing this function ever would have been. I mean, this function is not, you have to kind of think about what you're doing and make sure you're doing it all right. Nowadays, you basically write 3 lines. You create your URI signer, you say which user you're trying to sign something for, and you sign it. And that's it. And it takes care of everything for you. It generates, it does all the cryptography. It stores the keys. As you can see, the secret keys are not stored here in the code. They're stored somewhere else. There's a nice web interface where you can say, I want to rotate this key. It's time to get rid of the old keys. And you can switch your algorithm. You can say, I want to use SHA-1. Maybe somebody finds a flaw in SHA-1, and so we go and switch everything over to SHA-256 or SHA-512 or whatever. That's really easy to do because we don't have to change any of the code. We can just go do it in the configuration, which is stored somewhere else. And then checking the signature is just as simple. It's also 3 lines. So this is a really great API. It makes product engineers' lives easier. It makes my life easier because we don't have these bad security problems. And then this is all based around a centralized cryptography library. So again, it's the same thing. Like, let's make this as simple as possible to use, as hard to get wrong as possible. So these operations, the nice thing about building this cryptography API, at first we implemented it entirely in C++, in PHP. And then we decided, you know what, it would actually be a good idea to move this out of PHP and move it into a separate service. What this allows us to do is, originally all of our secret keys, even though they weren't in the source code, they were still being pulled into the web server. Because if you're going to do this in PHP, you need to have the key available to you there in the web server. So now we have a separate crypto service that if you want to do certain crypto operations, you actually go contact a separate service, and it has the key. And so the web server never even has access to it. So this has allowed us to make our keys actually more secure than they were in the past. Now, of course, we've got to convince everybody to use this library. I mean, hopefully everybody sees that it's amazing and just wants to use it, but there are still people who don't know about it. So we have a bunch of lint rules in the code base that check and see like, oh, are you trying to call MD5? Are you trying to call one of the encryption functions or something like that? And we give you a warning and tell you to go use our crypto API if you do that. So this brings me into another bigger topic, which is lint rules in general. So we have an interesting system for writing some of these lint rules at Facebook. We have this thing called Syntaxalgrep, which is, this is an open source project, so you can download it and use it on your code base if you want. What's cool about this is it allows you to write grep rules that are, instead of being text-based, they're based on the syntax tree of the PHP. So I can say something like, I want to find all calls to exec. I mean, these are the simple rules, would be all calls to exec. I want to find any call to system, any call to MD5, something like that. But then you can specify more complicated rules. And by the way, this is exactly the way that the rules are written. This is not, this is exactly what you type into Syntaxalgrep. So you can say, for instance, I want to find any instance where somebody calls implode, and the first parameter they pass is an ampersand. Because if they're doing that, then they're probably trying to build up a URI, and if they're building up a URI without using the URI class that we've created, then they're probably doing something wrong. So this is an example of how we could try to detect some dangerous patterns in the code base. This third one here, the ternary operator case, many of you probably know that PHP's ternary operator has the wrong associativity. So it's different from the way that it works in C++ and Java and all of that. So this is just something that we just disallow from the code base because it's just going to confuse people if they see two ternary operators in a row. But anyway, the point is Syntaxalgrep allows us to find these things really easily. We don't have to worry. It doesn't matter if there's comments in the way. It doesn't matter if this is spread out across multiple lines. Syntaxalgrep will find the problem for us. And then another tool that comes with this package is something called syntactical patch. So the idea here is if you have some change that you want to make to the code base, say you removed the second argument from a function and you want to remove that from all the call sites, syntactical patch can help you with this. So syntactical patch, you basically provide something that looks like the Syntaxalgrep thing, but then you say, okay, I want to remove that second line that contains the Y parameter. And you just run this across your code base and it'll make all the changes for you. So this has been really helpful for us in terms of doing code migrations and things where we wanted to change APIs. Okay, so back to security vulnerabilities. One thing that comes up a lot with a website, many websites are built such that you have a firewall and you have an internal network which has all the web servers and has the databases and all of that, and then you have the external network, the wider internet, and you want to keep those separate, right? You don't want to allow somebody outside your website to start making arbitrary requests inside of your network. So there's a bunch of cases where you have to be careful about this. One of these is curl. If you ever allow the user to control the URL that you give to curl, then they have the opportunity. Basically what somebody could say is, I'm going to give you a URL that points at one of your internal servers. And then your web server will go try to fetch this URL. And not knowing any better, it'll just go contact this internal server. Hopefully that you have authentication in place and stuff. So hopefully this isn't a big deal. But it's still a good practice to try to avoid letting anybody make these requests in the first place. It's just good to have sort of more layers of security if possible. So in this case, yeah, you don't want to ever do this where you pass a random URL to curl. So what we ended up doing, we just deprecated all of these curl functions basically and replaced them with our own curl library. So we have our own curl class. And the first thing you have to do whenever you try to do a curl inside of our code base is you have to say, I'm trying to access an external server outside of Facebook, or I'm trying to access an internal server. And the idea here is, well, if you're taking a URL from the user, presumably you would doing external. And so you specify external, and then the curl library makes sure that, okay, there's no way that you can make a request to an internal server. And so that prevents a lot of these problems. And obviously, if you're doing an internal request, well, hopefully you're doing that with a URL that you created yourself. So this dealt with a lot of the problems for us. This is a pretty good API, and honestly, it's a little bit easier to use, I think, than the old API because it's all packaged into an object, and so it's just a little bit easier to use than the standard curl library. But unfortunately, this is not all that you have to deal with in PHP. So we also have, there's also the fopen functions. So these in PHP, by default, these can take URLs. So this is something that we shut off in our code base. There's an INI setting that you can use to remove that. Not that you should be letting, again, not that you should be letting a user open an arbitrary file on your server, but again, this is just like adding extra layers of, trying to stop an attacker. If they happen to find a flaw, let's limit the damage that they can do. One interesting example that came up recently is something called an XML external entity vulnerability. So this is something that happens with libxml. Basically, whenever you're parsing an XML file, there's this way in XML that you can specify, okay, I want you to go include this external resource, where the external resource could be a file, it could be an HTTP URL or whatever. And so the thing is, this allowed, a guy actually found this, an external white hat guy actually found this and reported it to our bug bounty program. And we paid him a ton of money for this. This is the largest amount that we've ever paid out for a bug at Facebook. And basically what it boiled down to was this external entity thing, that he was able to find a way to execute or basically load arbitrary files so he could read our password file. And he was able to even make web requests inside of our network. And so this was pretty bad. Yeah. And fortunately, one interesting thing, anyway, we wrote up a blog post about it, and he did too. So if you're interested in that, you check out this URL here, which talks about how he found it and all that. But fortunately, this is a really simple fix. You just disable the external entity loader in libxml, and then you're done. So it's really interesting how just how many things you have to worry about, how many like this is something that's turned on by default that you wish was disabled by default because it's just kind of a problem waiting to happen. Okay, so the next question then is, we have all these vulnerabilities that we've talked about, right? So what do we do when we find a vulnerability on Facebook? How do we deal with that? So obviously, the first step is we'd love to just fix the code and push that code out and get that on the site. As I said earlier, we push the website twice a day, so we actually have a lot of opportunities to push fixes out to the website. If need be, we can do a hotfix, and we can push that out in about an hour probably to get that out to the site. But in some cases, an hour is still too slow. So one thing we built is this thing called Take Down the Site. And the reason we call it Take Down the Site is because if you misuse it, you could probably cause the whole site to stop working. So what this is it's a configuration variable that has a list of rules to run. And these rules are evaluated at the beginning of every request on Facebook. So as an example, this rule here says, okay, we're going to grab the HTTP host header out of the $_server, and then we're going to check it against this regular expression here. And if it matches the regular expression, which is to say, in this case, it has a dangerous character in it, then we're going to block the request here. And this allows us, this is something, again, that we were able to deploy in a matter of minutes to protect against a vulnerability. You don't have to go straight to blocking. In order to be safe here, normally what we do is we have a separate mode where we can say log anything. First, log anything that violates the rule. Okay, and then you can test the rule. You can test, first of all, is it logging everything? Like, does it look like it's going to take down the site? Or, and then you can test your exploiting the vulnerability, and you can see, okay, did that actually hit the log? Is this going to protect against what we think it's going to protect? And then you switch it over to block. So anyway, the whole point is you can do this in a matter of minutes. It's much faster than pushing code out to the site. So this is a pretty fun tool that we use. We don't use it a lot, but when we need it, when we really need to get a fix out quickly, it's really helpful for us. Another example of how you might use this is, suppose we discovered an XSS vulnerability a reflected XSS vulnerability on Facebook. What we would do is we would say, okay, let's check the get parameter. We'll take the get parameter here, whatever that's called, and then we'll check, does it have a less than sign somewhere in it? And if so, we would block it again to say that's a reflected XSS hole. Again, right, this is the kind of thing where if you did this, you would probably be rejecting some legitimate requests. There are probably people who would actually be writing, a less than sign somewhere in there. They would be writing less than 3 or whatever in their message, and you would probably be blocking some legitimate requests. But that's better than leaving the security hole, and you can try to push that fix in the next hour and then remove this hole or remove this rule and then go back to allowing everything. So the other thing here, as I mentioned, we have a white hat program. So if anybody finds finds a vulnerability in Facebook, we are happy to pay money for that as long as you disclose that to us responsibly. So this has helped us become a lot better in terms of knowing what things we need to be thinking about. What are the vulnerabilities that are easy for people to find that we don't know about? And it's just, generally, it's been a really good practice, and we've tried to be very open about this. These are the kinds of vulnerabilities that people are finding, and we often let people write blog posts about the things they found. As I mentioned, that guy who got the huge bug bounty reward, he wrote a blog post about it. So, it's good for him, it's good for us. This is the goal of the program. And finally, just one thing here. If you are interested in these web security topics, I think this is a really great book. It's called The Tangled Web. It's by a guy who knows tons of stuff about browsers and how they work and what all the quirks are that you can run into. So this was a great resource for me in terms of figuring out what things we need to be thinking about. And with that, one final plug before I start taking questions. Just as I said, I work in the London office. We have about 100 engineers in that office, and we are hiring. So if you're interested in that stuff, shoot me an email or go to our careers site. So with that, does anybody have any questions? And we're going to wait for microphones here. So.
Yeah, first off, do you have any sort of combats against click hijacking at all?
Clickjacking, yes. Okay, so clickjacking is an interesting thing. So the idea behind clickjacking is somebody takes one of our web pages and they put it in an iframe, and then they cover it up with something else that's usually a game or something that says like click here to get to see a video or whatever. And the things that we've done against this, almost all pages on the site are served with xframe options deny, which keeps you just can't attack it with that as long as we serve xframe options deny. The one outlier is all the social plugins that we put on other sites. So for instance, when you have a like button and you embed that on another site, that is something where we can't say xframe options deny because we want it to be on the other site. So this is an unfortunate thing, and it's not just true. It's not just a problem for us. It's a problem for anybody that has any sort of social plugin like this. But we invest a lot of time in trying to detect clickjacking. And so we have a huge spam fighting team whose job is to look for these sorts of things, to look for, okay, this is a URL that's getting shared a lot. And then, maybe one thing that you can look at, one signal you can look at is all these people, shared this or they liked it, and then they went back and they undid that later. If they deleted the share or they unliked it, or they later said, my account was hacked. And we can kind of correlate that and use that to detect these. So a lot of our time is spent trying to detect it after the fact, trying to block domains that are doing this. If we have domains that we know are spammy and are trying to use clickjacking, we try to keep users from going to those sites. So that's our general approach.
Do I have a second one?
Well, let's see. Yeah, go ahead.
I've got it. It's a relatively quick one. CSRF you were talking about. Is there any reason why you don't use it in GET requests? Is that purely a man-in-the-middle attacks?
So it just was easier for us to make that distinction between GET requests and POST requests. Basically, it's not a necessary distinction that you have to make. As I said, you could do this by just having every every endpoint controller specify I'm a write controller or I'm not. But we felt that it's just a little bit easier to do that with GET and POST requests. In particular, one thing we were worried about with a GET request is if you put a GET request, if you put the CSRF token in a GET request, then it ends up in the URL in the address bar, and then the user might copy and paste that and send that to somebody else, which would reveal their CSRF token. So the nice thing about a post request is the CSRF token is never there where the user can copy it. So, yeah. All right.
Yeah, just a quick follow-up on the CSRF attack and get some posts. I mean, obviously, a write is going to be really bad on that sort of attack, but does a read, is there a risk of sensitive data exposure or disclosure?
No.
Is that a concern?
Right, so this is an area where the browser helps us, actually. So the browser security model basically says, if an external site tries to make a request to Facebook, they're allowed to make the request, but they can't see the response. They can't see the results of that request. So there's actually no data, there's no danger of the data leaking to another site. Fortunately, yeah. Yeah. Who else do we have? Do we have any other questions out there?
What's your impression on security about WhatsApp?
That is a good question. So I don't know the answer. So generally what happens with these is the security team gets to look at the code, a week or so after the deal actually starts. In this case, I do not believe that the security team has had a chance to look at the code, so I don't know the answer. I honestly would be speculating. But I would say the one good thing about WhatsApp, I mean, Facebook is a very complicated website where there are lots and lots of endpoints, right? WhatsApp has a very small set of features and it has a very small, therefore it must have a very small set of endpoints that are exposed. So I would hope that means it's not too hard to actually check the security of WhatsApp, but I honestly don't know the answer. Yeah. But like anything else that we acquire, any acquisition that we make becomes part of our bug bounty program. So go start looking for problems. Anybody else? Is that it? Oh, back there in the...
How do you handle incoming user data? Like post requests, GET requests, anything like that? 'Cause you're talking about escaping it on the database abstraction layer, but do you do anything before that, or do you just allow your developers access to the GET and post super variables?
Right, so our approach has been to generally, we don't do any sanitization on input, except we do UTF-8 sanitization on input, just to make sure, because everything on Facebook is supposed to be a valid UTF-8 string, but otherwise we allow any characters. We kind of take the approach that people should be able to discuss whatever they want on Facebook, so they should be able to put less than signs in their, and talk about HTML tags in their posts, and we should handle that correctly. So there's no sanitization on input. And one of the reasons that this is important is because, honestly, if you try to, I think sanitizing on input is really hard because there are so many different ways you can try to use the data. Since you're trying to use it in a SQL query, you might try to use it in HTML, you might try to put it into JavaScript and then put it into HTML, you might try to put it into a CSS rule. And so trying to cover all of those with a single set of rules is really, on input, is really, really difficult. And so we've gone with the approach of always escaping things on output rather than trying to deal with it on input. Does that answer your question?
Yes.
Okay, cool.
I think you mentioned one of the tools was on GitHub there. Are any of the others available at the moment?
So most of these, unfortunately, are really tied strongly into our code base, and we haven't found a way to pull them out separately. I think maybe, some of them, XHP is an example of something that we have open sourced, but I don't know if we've done a good job of maintaining that open source counterpart. And one of the reasons that's been weird, honestly, one of the reasons it's weird is because we released an extension that worked for Zend, and now we use HHVM instead of Zend. So it's actually baked, XHP is actually baked into Zend, and I think there's an effort to open source that library and make that work well for everyone. React.js, which is, I mentioned this briefly, but we do a similar thing to XHP, that is entirely open sourced, so that's there. Other things like, our CSRF framework, that's the sort of thing that's really tied into a lot of hooks into our code base that would be very hard, I think, to pull out and share with other people, unfortunately. But anyway, it's something we should definitely continue to think about because I think it's valuable to help other people. Yep. Is that it? All right, cool. Thanks, guys. Thanks for coming to my talk.